Okay, welcome to today's talk at the Center for Information Technology Policy. Today we're very fortunate to have Professor Doug Sicker from Carnegie Mellon joining us. Doug is a chair of engineering at Carnegie Mellon. He's also the department head of engineering and public policy at CMU. He has held many positions in industry, academia, and in government in various advisory roles. One of the things I like about Doug's profile is he started his, before he was in academia, and he was actually a director of network architecture at Level 3. So he was an engineer of a very big backbone ISP. So we used to run in circles together in operators group conferences. Since then, Doug has had a number of advisory roles in the government. He's advised Department of Justice, the FTC, the FCC. He was the CTO of the Federal Communications Commission and has served on a number of advisory councils to both the FCC as well as many other organizations as well. So without further ado, I will let Doug talk to us about the radio spectrum, of which there's many things to talk about in the intersection of technology and policy.
Thanks, Nick. Great. So thank you for having me here today. I just spent an hour or so in the other room talking to some of your faculty, and you have a really interesting program here. And it's neat that you can be completely focused on the communication technology policy space. What the program that I head at Carnegie Mellon is much broader across the engineering domain. And in reality, it's really focused on energy and environment. So it's nice to be with folks that are closer to my space, like you all. So thanks again for having me. So here's a quick overview of what I want to talk about. I'm going to do a quick primer on spectrum and radio. You guys will laugh. This is super high level sort of thing. These guys are radio folks. Then I'm going to dive in and talk about the last 15 years or so of spectrum reform. And there's been some really interesting things that have happened in this space that really are culminating with some changes that have really happened just in the last couple of years. We'll do a quick look at radio evolution, looking at how radios are being designed differently. And then I'm going to do a deeper dive into a case study on a certain area of the spectrum that we recently freed. As a lot of arguments between different parts of the government and mostly the Department of Defense. Then I'll talk about some challenges and opportunities, but we're going to first do a quiz. Before I jump into the quiz, I want to mention this is going to be at a high level. If anybody wants to do a deeper dive into the technology things, feel free to reach out to me. I'm happy to talk about them at any level. Okay, so what is this? I brought props. Anyone recognize what this is? I'll let you see what it is. This is a hushaphone. Anyone know what the hushaphone was? Play with it, look at it. You can't hurt it. So hushaphone was a device that was made to attach originally to a candlestick phone. The old Bell system phones that you held, nobody probably ever used them for real in here. But it's the old phones where you'd go like this and you would talk into this little thing. The whole idea of it was that if you would attach it to the phone at this point, you could have a quieter conversation. So it's a waveguide. It's an acoustic waveguide if you're an engineer. But why this is an interesting issue is that the Bell system fought the attachment of this device for decades. They said that it was going to cause undue harm to the network. It was going to overload the system, all of these sorts of claims. The FCC agreed with them. It wasn't until a court case that overruled the FCC that said, oh, wait, this is crazy. You can attach this to the network. It's not going to cause harm. Some years later, this was attached to the network. This is called a Carter phone. So the Carter phone decision, which some of you may know if you've been interested in the public policy space. This too attached to the telephone network through a cradle. Looks like an old acoustic modem for those of us who played in that space. So you would hang your phone onto there, and it allowed for an intercom system to communicate into a radio, into a walkie-talkie system. This was important too. The FCC finally did agree, and why I mentioned this was that if it wasn't for this, you wouldn't have what's called Part 68 connections. Part 68 connection is what allowed you to eventually attach like an analog modem to your network, which back in the day was how you got on Earthlink and AOL and all of the early internet. So the early commercial internet was very, very dependent on this decision that was fought tooth and nail by the FCC. So an interesting couple of examples. Here's another one. I'll tell you just quickly what this is. This is the power mask of ultra-wideband. And the only reason I mention it is everybody who had spectrum was fearful of what ultra-wideband. Ultra-wideband is the idea of spreading a signal across a very, very wide band of the radio frequency spectrum, which I'm going to define in a second for those of you who don't know what that is. And lots of incumbents came out fighting, kicking, and screaming. This is a TV whitespace device. And TV whitespace, I think there's some people back who are looking at the device right now. This is a whitespace device, if you've played with any or not. And the broadcasters hated this idea. This was essentially a device that was going to sit in unused broadcast spectrum for mobile broadband services. So my whole purpose of this slide is that incumbents tend to really resist innovation in the spectrum area. They tend to come in pretty heavily with their arms swinging. And we've seen this many, many times. So my talk today, I really want to talk about radio spectrum. It's a scarce resource, and it's in huge demand. I'll show you that demand in a moment as well. So what I want to do is talk about ways to improve access to this resource. But first, let's do a little primer on spectrum and radio. I'm going to use these terms synonymously, whether I say spectrum, radio spectrum, airwaves, radio waves. I'm talking about the same thing. And what I'm talking about when I say radio spectrum is this range or this continuum of waves of electromagnetic radiation. And when I say electromagnetic radiation, what I'm talking about is this energy that's emitted by a charged particle that produces waves. So the way I'm thinking about this is if this is an antenna and I apply a charge to it, it's going to radiate. It's going to radiate a wave based on the characteristics of that antenna. Certain sizes of the antenna and certain other things influence how that antenna radiates and at what wavelength, okay? Now here's my little toy example. I just did this up. This is just to depict two radios that are communicating on a certain wavelength. You can see that's the wave, that's the spectrum, animation of the spectrum. We have two other radios. They're separated from each other. When they come close to each other, they interfere because their waves are the same wavelength. Now we have two different wavelengths. Now when these radios come near each other, they don't interfere. What this is supposed to show you is just two very simple ideas, one of which is if you want to reuse spectrum, radio spectrum, this energy that's emitted, you can separate them by space. The other easy thing you can do is separate them by frequency, because the frequency of the devices communicate are really dependent on this antenna configuration. So again, very small, quick snapshot about radios and spectrum, and we're going to move on. What happened in 1912 that's related to the spectrum space? Titanic. Did you know that the Titanic was instrumental in radio spectrum? The reason is there were these little capes that were sticking out close to where this occurred. There were a bunch of radio operators at the time, and radio was the Wild West back then. People just kind of communicated where and how they wanted to, because spectrum really wasn't assigned in the way anywhere near how it is today. And as a result, communications was getting garbled at the station, at the ship, as well as at the folks that were being sent out. As a result of this interference, it's very clear that there were additional lives that were lost, and that led to congressional action, which led to this Radio Act, the first Radio Act. And the first Radio Act produced the first attempt to manage the radio space, to say, hey, these certain ways, this certain range of frequency should be used for this certain thing. These other ranges should be used for these other types of services. So, yes?
So is this like just the U.S. or, did Europe have any interest in this?
Yes, and it followed suit. As you can well imagine, but the U.S. started the radio spectrum management and what was called, eventually became the spectrum allocation tables. So this was the event that keyed it off. It started, again, very simply as a set of rules and a set of restrictions on certain access.
But I mean, wouldn't this need to be international to help with the...
Absolutely.
Yeah, okay.
Yeah, you'd have to coordinate internationally, and it continues to be one of the tough things in the spectrum space. So if you're a country, for example, that's bounded on all sides by other countries, the U.S. is to some extent. We also have big swaths of ocean on either side. But we have to coordinate with Canada and with Mexico. We also have to coordinate with other countries because of some of our affiliated territories. But in Europe, it's even more of a challenge. So, but yes, indeed. Where's my hushaphone? Is it still here? Okay, good. I don't trust Nick. So, spectrum management started out very simple. As I said, it was really to prevent things like, hey, don't step on these safety of life sort of radio services. But over time, and over about a century of business and technical innovation, it led to this. This is the spectrum allocation table. And just to give you a sense of how deep and voluminous this is, some of these things in here are services that we know, some TV services, radio services, and there's a log function here. That top one, at the very top, there's 10 of those in here, there's 10 of these in here, 10 of these in here, 10 of these. So it goes down, and here we're in the gigahertz. This is the hundreds of megahertz, and that's the low frequency. I want to impress one thing upon you, which is I'm going to be talking about a spectrum auction that occurred about 2 years ago, and it's this little bit of spectrum right here. It sold for $44 billion. Didn't sell. It was auctioned for $44 billion. That. Okay, so spectrum, valuable resource. So digging back into some of the more recent evolution in spectrum, while I said first things happening with the 1912 and subsequent acts, some spectrum management occurring. Now it's wrong to say that there was 80 years of nothing that occurred, but there wasn't a lot of big things that occurred. What happened more and more was that people became more wedded to this process of assigning certain services to certain spectrum bands. So this is, again, an allocation table. An allocation table says this little slice of spectrum is for this service, like radio telemetry. This little slice is for FM radio or something like that. These little slices are for mobile broadband, so your Verizon type services. This process of allocating and cutting and slicing and dicing the spectrum is great for ensuring that everyone has their own little playground to play in, but it really is like the opposite of what we would think in the networking space of like statistical multiplexing. It's the whole idea is nobody plays with each other. You don't get to use it if somebody else isn't using it. It just sits there. And when we look at the spectrum, which I'll get to later, there's huge swaths of the spectrum that aren't used. And this is one of the reasons that a lot of the policy I'm going to talk about came into being. But again, this very fixed conservative command and control model of radio spectrum is where we started and grew into it more and more. And now we're trying to undo it with some of the technology and policy changes. So here's really where things in my eyes got started, which was with a task force that was created at the FCC. This really generated out of the Technical Advisory Committee of the late 90s. And while the report itself didn't have direct impact, it started the ball rolling. And what this report said was, hey, we need to move away from this kind of command and control toward more flexible approaches. It also said, hey, there's a lot of white space. White space is frequency that may have been allocated and assigned for a certain use, but that isn't being used. That's sitting there. And boy, why don't we try to figure out a way of using that? And the other thing that was realized was that there's a need to actually measure. And that idea of measuring, when the incumbents hear that, they tend to not like it. You can ask Nick. This is one of those things when anytime you say, I'm going to come in and measure what you guys are doing, folks tend to get a little uncomfortable about it, because the realization was the folks who were sitting on spectrum and not using it were going to be exposed. And that's exactly what happened subsequent. So there's the first really big, important policy issue. The next really came some years later with the National Broadband Plan, which is what dragged me back to Washington in 2009. And this was a congressional mandate through the Recovery Act for the FCC to look at how are we assuring that Americans are getting broadband access and getting it fairly and at a good price. And it launched a lot of different efforts, including deep dive look at spectrum, deep dive look at measuring broadband, deep dive look at changing or reforming the subsidies so that you could use subsidies for helping deploy more broadband services in America. So it was really focused on looking at broadband as like this next great infrastructure, just like as electricity and just as highways and everything else have been these great infrastructures. The focus was, how do we think about broadband as that next great infrastructure for the states? So within it, as I mentioned, was this policy chapter. I worked in the policy chapter and on the research chapter. And the findings were really along the lines of, hey, there's a problem. We don't have enough spectrum. We need to transform policies so that we can have more access to spectrum. And we should do that through through a few things. The one was we need to be more transparent about how spectrum is used and who's owning it. And as a result of that, there are now you can go to the FCC and through a web page look at different spectrum bands and see who and how it's being used. But you couldn't do that before. There's incentives that have changed. This one thing I'm going to talk about in a little bit is called the incentive auction that some of you may have heard of. It's this idea of trying to convince the broadcasters to sell back their spectrum so that it can be repurposed for mobile broadband. I'll come back to that a little later. A lot of, we had sections on access, like the use of new technologies, but really that kind of fell to the wayside because the real focus of the broadband plan wasn't on probably the spectrum that we mostly are using, like you're all using right now, which is Wi-Fi spectrum. I'm not criticizing you for doing your, it's okay. You looked up at me. This was really about licensed spectrum. So this was about freeing spectrum for services like that this run off of, right? Your cellular, your 3G, 4G type spectrum. So that was the second of these big reports. Now, as much as this was really being pushed by the broadband providers, this other report, which was called the Pcast Report, was really being pushed by the Googles and the Microsofts and the others of the world, not the incumbent broadband providers. And what this report was about was trying to look at things a little differently and saying, hey, this process of trying to go into the spectrum allocation table and find something that's not being used so well and clear that and move the people who are there or services that are there somewhere else, that's going to come to an end because it's starting to fill up. It's starting to become more and more contentious, and trying to do that's becoming more and more resistant. So this report, and by the way, I worked on this one too, the norm should now be about sharing, not exclusive use. And if you remember that chart, that allocation table, it was all about exclusive use. It's the idea of how do I allocate to a certain service, and then how do I subsequently assign it to an individual use or user. This report came at it as, why don't we find a very, very large swath of spectrum, maybe 100 megahertz, or 1,000 megahertz really, and assign it in a more open way. So let's find big, big bands, and let's say you can play in that space as long as you maybe abide by the rules like the Part 15 rules that govern how your Wi-Fi devices operate, which essentially is you can't cause harm to others, you can't call foul if you're harmed, you can only operate at a certain power level. And we know with those simple rules that we've had this incredible thing called Wi-Fi occur, where this unlicensed spectrum has been incredibly useful for us. The report also focused on this new technology, and this is what the rest of the talk is going to be about, looking at how these new technologies are coming out. Please.
Two little questions. First, is this report public?
Oh yeah, these were all public reports.
Second, you say that the norm, you argue that the norm should be about sharing or exclusivity. It's not yet implemented, right? What are the, you want to talk about that later?
Yeah, so there are some areas where we're seeing moving away from exclusivity, and I'll explain those in a little more detail as we dig in a little later. This is still not the norm. The norm still is exclusive use spectrum. And when AT&T or another company pays $44 billion for spectrum, they're pretty much wanting exclusive use to that. That's kind of the expectation.
Do you think it's the beginning of a big shift?
I think it's the beginning of a shift. I think it's going to take lots of baby steps to move from where we are now, because there's a lot of entrenched incumbents. And if you remember my first set of slides, right, incumbents fight these sorts of things. So we will see resistance. And by the way, I'm not, ironically, at some level, the AT&Ts and Verizons and T-Mobiles of the world are looking at this technology in ways that others aren't. So they're on board. They're trying to get ahead of it, and they're trying to understand it. There are many incumbents. When I say incumbents, I'm mostly actually talking about broadcasters, television broadcasters, which I'm sure almost none of you actually watch broadcast television. That's just not how we consume TV or video anymore. And I'm talking about large government agencies such as the Department of Defense, who are sitting on swaths of spectrum. But it is still the norm is still exclusive use. Okay? So really together, these three items, if you want to read three reports that have really kind of set the stage for like the last 15 years and probably will serve as a guide for like the next 5 years, I would encourage you to read these. I'd certainly encourage you to read the Spectrum chapter in the National Broadband Plan, as well as the Pcast Spectrum Report. This is really kind of forward-looking, very different from the classic model, and is really proposing things that are, toward the future. So shifting back into the technology, and again, I was asked to not go too technically deep, but it looks like we have a much more technical audience than I anticipated, but I'm going to try to keep it still at a high level. What are the things that we can do in terms of tools for getting access to spectrum? Well, there's three things really. The first is to reallocate. I mentioned that before, and when I talk about spectrum reallocation, what I'm talking about is going in, finding a band, and reassigning it for a certain service. And this has been how most of what we think of the 3G and 4G spectrum, it's been gotten through this reallocation process. The problem is it takes a lot of time, and it takes a lot of money, and it's becoming harder and harder because the low-hanging fruit that on the spectrum allocation table, the things that were kind of obviously not being used and were in good range of frequency spectrum have already been reallocated. There is some effort, and here again I mentioned this word incentive auction. I might as well just, I'll do it now and skip that slide when I come to it. Does anyone know about the incentive auctions? Anyone know what it is? Can you explain what the basic idea here?
As far as I know, taking the spectrum from the broadcasters that are not broadcasting in some region and allocating that for mobile communications.
Okay, that's right, but there's an important thing. You said taking it from them, and I want to make sure that people aren't thinking it's some...
Of course, by their consent, I guess.
Right, so the idea is federal government, the FCC, has an auction in one direction where they buy back the spectrum from the broadcasters. So they go out and they say, hey, broadcasters, tell me whether you're willing to sell your 6 megahertz of spectrum. And the FCC's job is to try to see if they can, the FCC's job is to see what's the lowest price that they can get spectrum in each of the regions, right? Then the FCC, after they complete it and they say, you win, I'm buying your 6 megahertz in New York City. And you probably are going to make big bucks because it's in New York City and it's 6 megahertz of spectrum. After that, the FCC is going to do two things. First, it's going to reorganize, it's going to repack the spectrum so that those bands can be useful in places where people want to have LTE service, 3G, 4G and 5G services turned up. So there's a repacking effort that has to occur of the spectrum. But also then it's going to turn around and it's going to go to the mobile broadband providers. These are the ones who will pay billions of dollars for the spectrum. And they'll say, OK, I have spectrum. Buy it from me. So it's arguably a win-win in that the broadcasters should get the money that they want for the spectrum. It's not a taking. And the mobile provider should get what they want, which is spectrum. Great idea, really interesting. Hasn't been as useful as we had hoped. Yes, and you and then.
Presumably it's not legal for the broadcasters to go directly to the mobile.
No, they're not. Yeah, but I like that you would think of cutting out the middleman. In terms of what the dollars that are expected, we're just just Tuesday was the close of the one side. So the broadcasters set the prices by what they're willing to let go their spectrum for. They'll say, I'm willing to let it go for $200 million. Let's just say. I don't know what it is. It's probably much less than that. And then the FCC, after it shifts everything around and repacks, it's going to turn around and it's going to say to the broadcasters, okay, what are you willing to pay for the spectrum in this rich area where you've been wanting it? So the broadcasters set their price, the mobile broadband providers set their price. And by the way, and this is an important thing, then I'll go to you. That money does not go to the FCC. That money goes to the Treasury. People are always like, the FCC has all this auction money. No, they don't. It does not go to the FCC. It goes right to the federal government. I think Jen, and then you. I'm sorry.
So one quick question on what you said, but I'm also curious when spectrum is auctioned off, is there any time limit on how long the carrier can have it? And then the second thing you were just talking about, where does the FCC get the money to buy back the spectrum?
So there's a little bit of a you can imagine there's a little bit of a delay, right, in terms of you'll get your money when, yeah. But there's also means of covering that in the interim. I think they can dip in somewhere. To answer the other question, which was,
Is there any
oh yeah. So this is a great question, and one of the problems that exacerbated that problem of that table, right? Because a lot of those allocations and then the subsequent assignments were, so the allocation is kind of to a service, and then there's an assignment that's for you. Nick gets this 10 megahertz. A lot of those were made in a way that didn't have the lease didn't end. There was no time limit to the lease.
really is selling, not
Arguably, yes.
Well, they weren't sold,
That-
they were given away.
Yes, that's right. And a lot of the spectrum was, before the auctions, there were what they called beauty auctions, where it was just there was no money, but it was like, we're going to give it to this one. And broadcasters received the spectrum originally free. So a lot of that has changed because broadcasters have transferred licenses, which comes with it. But nowadays, there's an attempt to put in place these structures that say that it's a lease of 10, 20, whatever years, but it's still problematic because you can imagine if I build out a whole network infrastructure around this, be that towers or handsets, and now you're going to tell me you're going to take it back. It will be a challenge, and it remains a challenge. But it is that resource is a government resource. Is that it is a lease that you have for some period of time. That time might be infinite.
Yeah, so kind of on that topic and also on Nick's question about cutting out the middleman, how do you enforce that? Because I could see that you could either kind of enter some informal, like, leasing agreement with where I don't remember, like the TV guys have it and the cell phone people want it. And so you just be like, hey, yeah, pay us a lot of money and we won't say anything about if you're using our
Yeah, but so once the FCC found out about it, it'd be in the courts, and yeah, and it does get to an issue. Sorry, that's me. You can imagine one of the things that comes up is how do you enforce any of these things? Ironically, over the last 30 years, the FCC's enforcement capability has been completely cut. There's very, very little enforcement capability. But something as outrageous as that would be easily realized. First of all, you're going to have to get a device that can operate in those bands, and those devices essentially are approved by the FCC. So there's lots of reasons to believe why that wouldn't play out. Now I'm going to try to covertly, not so covertly, turn down my volume. Okay. So second tool that we can do, and this is something that electrical engineers and physicists of the world and computer scientists of the world have been focusing on for the last 40 years, is you can improve how the efficiency of the system or the device. And that means moving toward smaller cellular architectures, for example. So when cell phones first came out, the coverage of a cell phone from an antenna was very, very broad. There weren't a lot of users, and there wasn't a lot of data, so you could do that, even with a little bit of spectrum that was there. But as we had more and more users and higher data rates, you had to cellularize it. You have to have much more dense cell architectures. That's a costly matter. Putting in additional cellular infrastructure is very costly. That's one of the reasons why the mobile broadband providers would rather have spectrum that they could throw at the problem of data. Another thing is spectral efficiency of the devices, improvements in modulation and coding in ways that things, kind of at the physical layer. This has gotten better and better and better over the years. When we look at, old cell phones compared to the efficiencies of LTE, it's remarkable how many bits per hertz can be gotten out of this technology. And there's other things that you can do to improve it. But here again, this, just as reallocation is getting harder, improving efficiency is getting harder as well, because the great efficiency gains are having smaller and smaller return. So then the next tool, and what then the rest of this talk is going to be about, is really about sharing. So while we've always shared spectrum, if you remember in my little toy animation, we either share spectrum by moving away from each other in frequency, in terms of the wavelength, or we move away from each other in geography. We physically move away from each other in space. But what has changed with the introduction of new technology is how we do that. How do we think about moving away from each other, and how aware are we of whether you exist or not. So through simple things such as, do I sense that you're in a certain area, or do I can I dip into a database and find out whether in where I am right now, whether somebody's using spectrum. Just those two little tools, sensing and the use of a database, can free up access to a lot more radio spectrum. So the one thing I wanted to talk about, though, and make sure that you understand, is this issue of allocation. So I already showed you this, right? This crazy, highly divided, allocated, and assigned table of the spectrum. But if we zoom in on just a little slice of it, and this is a little slice, you can see that it looks pretty densely crowded with radio location, fixed satellites, some aeronautical thing. I can't even read all the rest, but radio location, on and on and on. When we put that, yes?
What does it mean when you have multiple items on the same?
There is some mode of sharing that's being done already. Either it's coordination within that band that you're channelizing, so you can think of it as subdividing that space, or it's geographic. Generally, it's not time. Time has not been something that's been very well used in the spectrum space because of the difficulty in coordinating that. We'd use time all the time in the networking wireless space, right? It's kind of, time division's a normal thing. But anyway, let's now look at that. This is that thing that I just had on the other band. And this little plot, the x-axis is frequency. So these are in gigahertz, 1, 2, 3. So, and on the y-axis, it's power in decibels. Okay? So where you see something, that means there's a service. Where you don't see something, there's no service. Okay? And these were actual measures. And I'll show you some other actual measures later. What you should be able to infer by this, and these were averaged measurements as well, there's a lot of spectrum that's not being used. And it's spectrum that in areas that are of interest. And while that showed spectrum across the x-axis, so we were looking at whether a frequency component had use or not, here's another way of looking at it. This is that same kind of idea but a different frequency range of frequency across the x, power on the y. Here, if we look at it as what's called a waterfall plot, where we have time on the y-axis and frequency on the x, what it shows is there's a spot. It didn't come out very clear. It's great on my screen, but this is showing use, but this is no use. So what the waterfall plot is showing, again, because this is time on the y-axis, is that, oh, well, when I look at this, I would say, oh, I can't use that. There's somebody there. Well, not always. Turns out that it's time dependent. So both of those things represent holes or white spaces or opportunities for using the spectrum space. And, but it's important when you do this, you have to figure out how to do it right, because if you get it wrong, you could end up stepping on them, or you could think that you're at a white space, and then all of a sudden they come back on and you're stepping on them. So you don't want to do that, because then you're going to be interfering. And of course, we don't want that, and you particularly don't want to interfere with an incumbent, because they're going to squawk the loudest if they find out. So now let's, yes, Nick?
Quick question about your measurements here, and then particularly maybe the next one with policy. I imagine this might vary wildly depending on where you're doing it.
Absolutely.
So do you have, when you're presenting these types of things, do you have to go to the middle of New York City to take your measurements? Or what's the story with variation across geography?
Yeah, so it varies greatly in terms of geography. It even varies greatly in terms of geography and what particular elements of frequency. Not surprisingly, where it's denser population, you're going to have more people, but not necessarily. There's other areas where, because there's an airport nearby, for example, or because there's a certain farm use, or certain other radio location, radio astronomy, middle of nowhere, right? there could be uses of the spectrum that otherwise you wouldn't. But you're absolutely right. This is not, it would not be fair to go to the middle of North Dakota and take all of these measurements and then try to apply that data to an algorithm that you'd run in New York City. So completely the case. And it's one of the, that's been dealt with as we get more deeply into it through this idea of where are you, geolocation, GPS sort of data. Where are you at some certain time? And what are you hearing? So, and I'll talk about those two models in a little more depth. But yeah, absolutely, that's right. So I want to talk again, and this is at a super high level, looking at some of the technology innovations in the radio space over the last, I'd say last 10, 15 years. Traditional radios, when we think of, and by the way, when I talk radio, I am talking about these things, not AM, FM radios. I hope that was clear from the beginning. Probably should have said that. Traditional radios, whether it's a walkie-talkie, even early cell phones and other things, very much defined in its operation through a bunch of hardware components, piece elements of, what we would think of as, if you were at electrical engineering, what you would have put on your breadboard when you were trying to make little things in your undergraduate class. So all kinds of resistors, transistors, and various elements. So very much defined in hardware, very fixed in its operation. A traditional radio, you turned it on, you turned it off, you had a volume control, and you could change the channel. When you did all of those things, you were making changes in terms of the radio circuit or the radio chain as it is instantiated in hardware. About 20 years ago, a trend started. It really took off about 15 to even just 5 years ago. This thing that's called software-defined radio, and this is what I've done a lot of my research in the last 15 years. The computer architecture and what you can do with these. So the idea here is all of these elements that were in hardware, the radio chain as we talk of, from the antenna all the way down to the processing to the speaker, if it's something that's a walkie-talkie kind of app. Much of the functionality that's in the middle here is put onto a computing device. So it's enabled through a computer that can generate and understand these radio signals. So it's going to take in a radio signal at one end, and it's defined in such a way that it's instantiating what used to be hardware elements on software. On the board and software. By doing that, I can now alter how this computer is programmed and add flexibility. I could change the channels not by using different hardware elements, but rather by changing the configuration of the hardware and the software that's on the device. So, and this is one of the boards that I used to work on at Colorado. So now I'm going to have a little more flexible behavior, and I can potentially even accommodate anticipated events. So this, again, a toy example, if x is greater than 1, then change frequency, otherwise stay. So if x is greater than 1, maybe that signals that an incumbent has come back. So this would just be a simple algorithm to say, hey, abdicate a certain spectrum band because I'm getting signal from somebody else. So again, the real change that has occurred, though, is that you're moving from a hardware-controlled and defined operation to a software-controlled operation. Yes?
So, but even in the hardware, you said that you could change frequency. So the idea with the software-defined radio is that the device can have some built-in sensor to set X to 1. It can detect if the incumbent is
really, I missed what I wanted you to get. It's really that I can reconfigure this because it's simply a computing device. So I can change its configuration and I can do that in many, many ways and probably much more flexibly than I could do it on there. And I could do it here in a way that doesn't require me to reuse anything. I don't have to have a whole nother chain of this hardware elements. I just change how this thing has been, how this thing has been programmed to operate. So I can also, the way of thinking about it, which is interesting, if I make a mistake in this thing and it goes out into the public, it's out there. If I make a mistake in this thing, it's possible that I could do a firmware update and change that mistake. There's another thing, which is if I have one of these radios that operates at a certain frequency band or for a certain type of modulation, for example, and I want one to operate in a different, I would probably have to replace that element. It's possible that I could do that in hardware, maybe with the attachment of a different antenna here, and preserve the device. So these are all things. It's really about the flexibility that moving toward a programmable environment provides, which is really arguably what the whole PC revolution and a lot of these other things have provided us too. It's a general purpose computing device, and I can do all kinds of stuff with it. This is a general purpose radio device, and I can do all kinds of things with it.
Yeah, so I definitely get the general, like, with software-defined networking, same thing. But I was just confused about what exactly, how fixed is fixed, I think, is my question.
Well, how fixed is very fixed in a hardware radio. If it has not been pre-programmed, there's, you know, if I haven't built out a certain set of hardware connected elements from one to the next to the next to the next, I'm not going to be able to instantiate that and change the operation. The question is, and this isn't unlimited, this one here, this isn't, you know, it's not like I can do anything on this. But if I can figure out how to program an FPGA with the elements that I have already in it to do something differently, then I have more flexibility here. And again, I can take advantage of that flexibility by having some simple logic running on here that says, oh, in this condition, use this part of the FPGA. In this other condition, use another part, or maybe change its parameters and change its operations. Okay. Okay. So while not necessarily requiring a software-defined radio, but it does make it a lot more fun, is this other thing I've done a lot of work on, which is called these cognitive radios. And the AI community hates this term, cognitive radio, because the radio is not cognitive, it's not aware in their sense of the word. But you can imagine that if I have something that's programmable and that's flexible, and if I wrote code that would say, hey, I'm going to tell the radio, here's the things that you need to think about. I'm going to have a little policy engine that says, generally, when you are here, or when you are in the presence of a certain signal, you should behave a certain way. Otherwise, you can do other things. And so I can have a set of policies that will define the operation of that thing. I can have what we call cognitive engine that can also dictate how that might operate. And I can start doing things like I can start sensing my environment and remembering certain things. Oh, every time I'm here at this certain GPS coordinate, I remember there's a set of interferers, and I probably shouldn't waste my time getting configured or sensing the spectral band because it's not going to be useful. So don't do that. So I can learn to adapt. I can learn to sense my environment and adapt around it. And I can stick that off in memory so that I can remember it for later. So we're now getting to a device that not only turns on and off, but it can turn on and off, it can reconfigure itself, it can sense what's going on around it, and it really starts adding to the capability of the radio. Now, one of the problems, and I'll get to a little later, is we still don't have very powerful versions of these in a form factor like that. One day. Actually, I say it here, you know, ultimately what you're going to want something that looks like that can operate across really, really wide swath of spectrum, maybe a gigahertz of spectrum. And you're going to want to do it, you're going to want it to be cheap. You're going to want it to be small. You want it to have processing power. You want it to work while it's moving. And you don't want it to interfere with other services. This is really hard. This is a lot of engineering. A lot of work still to be done here. Actually, it's more than engineering. It's physics and everything. It's material science. There's lots of stuff that still has to happen here to be able to get from where we are right now with cognitive radio capabilities, antennas, and other such things to something that's cheap and portable.
I was going to say, are there like FPGAs on that board or something?
Yep, it's a 3-core FPGA model.
So another thing on that list might be energy.
Yes,
right?
yes. I kind of threw that in with processing power, yeah, but you're absolutely right. A battery and other such things, right? So these things, you know, the ones that we build, my students would be out there with power cords, you know. This was not, but they're still really cool. I can tell you, the stuff that you can do with these devices is truly remarkable at this point. And the fact that a student, I mean, and again, this is one of those areas where it's interdisciplinary, but not as we often would talk about it. You need students who are good at EE and good at CS. You need EEs that can program, really program, to wrap their heads around this in a meaningful way, and that's a challenge in and of itself. There's elements of this that are exposed to the programmer that are pretty low level, and we've worked on trying to create interfaces to make it more CS friendly, and it's always frustrating. You never get what you really want out of it. So it's easier to just have them be able to deep dive. But you know, I've had grad students, even at the master's level, the stuff that they can do with these things is just remarkable. They'll come to me and they're like, oh, I've programmed up another modulation scheme. I've programmed up another, and they just knock it off. Now, the other thing you keep in mind is that it's not like you'd have to do that. It's not like the consumer would have to do that, right? It would be a set of library, it would be a set of functions that would be on there. But you know, from an academic perspective, when you're playing around in this space, there's a lot of heavy lifting to be done. Okay, so I know I'm going to run over, so I better step up the pace. Let's take a look at what policymakers are doing. It's moving slowly, but progress is being made. I'm going to walk through this really quickly. There's really two flavors in the kind of the dynamic spectrum space or the cognitive radio space. One is the database-driven one that I mentioned, and the other is a sensing-based approach. Now, of course, we've in the networking world, we've long had a listen before talk paradigm, but it's gotten smarter and smarter. And the first thing that kind of initiated some of this smarter and smarter was this thing called DFS, which was a smarter listen before talk. You had a period where you would check, you know, so this line is the new entrant, and this is the incumbent, and it's a radar system. So the incumbent would look to say, hey, I'm going to check for 60 seconds to make sure that a band is available. That might sound like a long time, but you know, there's reasons to have, you know, depending on where you are, Nick's question, where you are and what other service you might be interfering with, 60 seconds isn't so unreasonable. But in this situation, what happened is you can see that this radar came on. Okay, this is time across the y-axis, I mean the x-axis, right? So we have these signals. This device senses those because it has a match filter or something that can detect that pulse. And then it goes into this non-occupancy mode. It says, what it tells itself is for that channel that I was listening to check if it's available, I need to mark it as being occupied. So don't go in that band. In this scenario, it got beyond that. It was listening. It did the 60-second listen, and it said, looks like it's free. I start communicating. And what you can see is there are these data burst periods. But what's really important and what's kind of clever is these little gaps in between where you listen. And what that allows for is for detection of a primary that might come on at a later point. And this allows for, again, this what's called abdication. You abdicate that band and you move out of it. And it allows for minimal interference with an incumbent device. So that actually exists now. DFS is a technology that's part of the 802.11 world. It exists, and technology has been deployed. Much smarter versions of this sensing technology have been done as well. I was part of a project called DARPA XG, which really looked across a bunch of different bands and how we could do this more intelligently. And there's all kinds, for those of you who are EE-ish, I'd be happy to talk to you about some of the cool stuff that went on in that space to make sensing smarter and to really determine whether there's reason to try to occupy a certain signal for any period of time. The complement to this, as I mentioned, was this geolocation, or a database-driven model. This is the model of the TV white space, which says I'm going to, the device is going to identify its location and then do a lookup in a database. That database arguably could be in the device, but more likely it sits somewhere else. And that database could give me permission or provide me just the information I need to be able to find what channels I should get onto. So if I know that there's, like in this situation, if I know that channel 3 and channel, I guess that's channel 4, I don't know, it's a problem here. Channel 6 and channel 8 are taken, I know that 7 and 5 and 2 are free. So I would be able to make use of those channels, and I would get that information by dipping into a database. You might wonder, well, wait, why wouldn't I just do the sensing like you just described? Turns out, here again, the broadcasters, the incumbents, did not like this model very much, and they certainly did not want the device itself determining whether it should operate. There are legitimate reasons why. It is not foolproof. It's not easy for the device to pick up whether if it operates, whether or not it would interfere. For example, if that TV whitespace device that was trying to sense whether there was another, whether it was in the area of a received signal, if that was in a basement, for example, or somewhere else, it might infer that there's no other operating, that channel is free. And it might start radiating even at like a watt or a half a watt, and then end up interfering with a neighbor who had a high gain antenna pointing at that broadcast television. So legitimate reasons why this is a problematic sensing model, and why the broadcasters really preferred a database solution. So this is now out. There is TV whitespace technology out there. It's very slow going. It's very slow going. But it is the hope of kind of future generations, just like sensing is very slow going. And I do want to point out some of these changes, we probably won't see the fruit of this for 10 or 15 years. I think you asked the question before, which is, oh, is this already deployed? This stuff is getting deployed, but just like even Wi-Fi, for example, it took years for Wi-Fi to take off. Wi-Fi, the unlicensed spectrum, I shouldn't say Wi-Fi because that's a brand or a trademark, but the spectrum was allocated. It took quite a long time for that to actually start being used in any meaningful way. And now it's very well used, maybe too used. I already went over this with the incentive auctions, so I'm going to skip it. I do want to run through this. I don't know if I'm going to get a chance to get to my research topics, but this was something I was presented when I moved from the FCC over to the Department of Commerce. I was given this report. It didn't go out. This was while it looks like it's 95 megahertz, the only part of this spectrum that was of interest to the mobile providers was the first 25 megahertz. But the Department of Commerce, in cooperation with the Department of Defense, did a deep dive look at this range of frequency for reallocation. The use of the spectrum, which might raise a few eyebrows in here because it actually was for domestic use. Unmanned aerial vehicles, precision-guided munitions, tactical radar, covert surveillance, and other such things. The Office of Spectrum Management at the time which was an office within NTIA, said yes, they will be able to do this, but first it's going to cost $18 billion. It's going to take 10 years to clear, and the DoD wanted some broadcast spectrum. That last one is really probably the most amusing aspect of it, which is this is the gorilla and this is the elephant, or both of them are gorillas. I don't know how you want to, but this one hard to move, this one hard to move, and this was just like them going, oh, and even though I just told you a ridiculous number of years and a ridiculous amount of money, now I'm going to tell you something else that even is going to make it harder. So I knew about this band because I had measured it. Let's look at what the Department of Defense claimed was the use of this spectrum. This is all those circles, those crazy circles, are all the use of this spectrum. And here's Alaska and Hawaii. And what you can see probably is the only place where it's not being used is like North Dakota. It's part of Canada, isn't it? Which is really funny because I thought there would be military uses up there. But this was their claim. And here were the measurements. I had the NTIA folks go out because we had a measurement squad in Boulder that does all of these sorts of things. I asked them to go make measurements at different bases. Here again, okay, across the x-axis is frequency. On the y-axis is power. Here's that swath of spectrum. What it shows you is it's not being used. That's not to say that it absolutely isn't being used. There was some use of it. There's no question. There's a couple of services, DoD services, that were making use of this. But it was not 18 billions, and it clearly was not 10 years to clear. So first thing you should think of, given that stuff I was just talking about before, is this is a poster child for sharing. Let's not clear it. Let's share it. How can we coordinate with you so that you can keep where you're needing it, but mobile operators might be able to use it. So whole process started. First thing was looking at pure sharing. Is it possible? And it turned out for some of those services, the crazy services I just talked about, that it was possible for mobile service and the aerial services to cooperate to operate at the same location, in time and in space. The other thing was tolerance, and this is something that's a new area in the radio space, which is the idea of, well, this is what in the networking space we're all used to this, right? Which is a little bit of interference, the network keeps running along, right? We recover at layer 2, we recover at layer 4, right? We just do this, right? How tolerant is the application to some interference? And it has to be more than intolerant to any additional signal in the band, because that's just kind of crazy talk. So how do you even get to that point of where you have realistic conversations with incumbents to say, well, let's test it. Let's see what happens if we turn up a competing radio service in that space. And one of the first places where that happened was on my second week at the Department of Commerce. I got the report on light squared, and if any of you know in the radio space what that is, it was a spectrum that was going to interfere with GPS. And we went through a whole modeling exercise on that. But the other thing, the last two things are probably the most important ones here, which is an exclusion zone. If you know you're going to be using that spectrum in a certain area, DoD, and that's where you're also going to be using it, that will be part of the license. The operator can't operate in that space, and as a matter of fact, they can't radiate at it. They have to radiate away from it. So there's that solution through exclusion zone. And then the last thing, which is again the most expensive, as I mentioned before, is this relocation. How do I move that incumbent provider out of there? That was where you run into time and money. So at the end of the day, I'm trying to remember what I have. I don't know if I have. I don't have it in here, but we formed this committee up, this Federal Advisory Committee, and in 3 years, the bands were cleared. It cost a couple of $1 billion. It was something like 4, I think, billion, not 18. And that spectrum went in what was called the AWS-3 auction, which went for $44 billion. So that's an example of taking a different tact and thinking about sharing as the starting point rather than the exception.
Excuse me, did that end up with Defense Department sharing with commercial services, or Defense sharing basically within its own zone?
The former and a little bit. So it was there were places where there was sharing, and we realized that could work because of the nature of the operations. There were other places where DoD had an exclusion zone. So if we think of the whole map, there's still places, there's still tiny circles, not great big circles. There's still tiny circles where the mobile operator will not be operating in that area.
Why did Defense agree to this? Because, I mean, really, why did they have it?
They did not want to. It was a huge fight.
So they were told they had to.
We had huge arguments with them, and NTIA wanted to go with this. My boss at the time wanted to move ahead, and and a few others outside of the agency dug in and said this is ridiculous.
I guess I'm just asking, did the White House get involved in this?
Sometimes the White House, on that one, no. But on some other things, the White House, that's the role of the White House. What Ed and others can do in OSTP, they can look at it and go, wait a second. But even within the White House, you can imagine that there's going to be conflicting. Well, it's just like within Department of Commerce. There's times when NTIA wants to reallocate spectrum so that the FCC can use it, and you have NOAA or NIST or somebody else going, no. In the White House, you have national security that would be saying, no. But you would have OSTP going, wait, no, we know we can do this. It's all good. And you can imagine there's reasons for the Department of Defense to resist as well, which is at some point they're going to get squeezed to where it hurts them, right? And none of us want to see the Department of Defense unable to do their mission, but you also don't want them sitting on a scarce resource that could be put to a better purpose. So, it was an interesting endeavor. The others who got involved were the mobile operators, who came out and saying, boy, this would be great spectrum. We'd really like it, and it lines up with some world allocations of LTE bands. I'm going to try to get through this quickly. So still lots of neat stuff to be done in the device space. How do you make these receivers, like I described before, that have the power capabilities, have smart antennas, have everything else? Sensing versus geo databases versus none of the above. This is still a really hard problem. There's still broadcasters who are trying to sense at a very, very low level, which isn't practical, which is driving toward geo databases. But there's still people who are saying, wow, if we could do sensing, it would be a lot better and we could get better reuse. But they're going to demand such a high probability of detection that false alarms are going to cause this to be problematic. So the question is how do you get to more sophisticated signal processing, cyclostationary detection, and some of these things that you guys might know about. But to do that on a cheap device, super hard. This is one of the things that I think, from an interdisciplinary perspective, this and down here are really interesting. What's the enforcement model? What's the coordination? What's the validation? And of course, what's the security? Who's going to believe? So let's go back to that example with DoD. Why should I believe that you're not going to operate in my exclusion zone? Why should I believe that I can share? If I'm sharing with you and you interfere with me, what action should I take? What's the legitimate next step that I can, one, detect that you're interfering with me, because I might not even know that you're interfering with me. You might say then it doesn't matter, but it does matter. And how do I then mitigate that? So there are these steps that are tied up within here that go well beyond just a pure technical issue. And then one of the things that a lot of us are looking at in the radio space, which is we focused at a certain swath of spectrum from hundreds of megahertz to low gigahertz. And really, it might be that moving up into higher gigahertz spectrum is a more interesting thing, what's being called millimeter wave. So I'll throw this other one up, which is, these are all the things I'm working on right now. I'll tell you one of my fun toy projects. And this started as a, oh, this should take you a couple of weeks to a student. We all know these. What's the value of that whole table? And how do you even determine it? And let's just get a back of the envelope estimate. And what might it look like? What might it have looked like 10 years ago? What does it look like now? And what does it look like 10 years from now? I think it's when I added that last time series piece that really just but it's a really fun exercise to really think about, well, what's the economic value of this, even and what do we use as proxies for determining that? You know, for certain bands, we just say it's the auction. The auction has set the value. It's that much. That might be an underprice. It might be an overprice, but it is something that we can start with. Then with that, why I wanted to do that is I wanted to understand, if we start then understanding where sharing could go, what does that mean from a market perspective? Because it could be actually very negative. If we share a lot of spectrum, it could disrupt the markets. It could disrupt, expectation of what it costs to do business in the spectrum space. I'm very interested in this idea of how you define harmful interference and what that means at an application as well as a device. So how might we determine that as a meaningful metric? And this is going to be, again, one of those things that differs widely in terms of what's being interfered with. I talked a lot about this, but there's all kinds of better models, better measurements, better thresholds. I have students who are working a lot, some still at Colorado, on some of that thing, as well as this idea of real-time measurement. I'll leave the others off, but this is really where I'm working in the radio space. I also do work in other areas too that aren't spectrum related, but this is really what's occupying probably 60% of my research time.
We're going to have databases that coordinate use of spectrum sharing. I'm curious your thoughts on who's in charge of that database, and should it be distributed, should there be multiple companies involved?
Yeah, and
should it be regional, or coordination with boundaries? I mean, there's a lot of really interesting articles.
Yeah, there really are, and that boat has. So the databases are out there. There's a whole bunch of them. They overlap in region. The idea was some set of competitive services, competitive providers. There's some people you would expect who provide database. There's others. There's Microsoft and others who operate. Did you want to have something on that?
Follow up, yeah.
Yeah, yeah.
Any of our blockchain experts here right now. Has there been discussion of things like Ethereum and I think these cryptocurrencies that are good at asset transfer and management as sort of a decentralized way of managing some of this?
There's been nothing interesting at that level, but there's been a lot of talk about, are there other ways of doing this? And so I had tried to get some money to do why does there have to be a database? Why can't I be my own database? So the ultimate distributed database, and we all share with each other, and it's a massive. You can imagine the atomicity. There's all kinds of interesting things that would be going on in that space, right? But I could actually go back to that distributed database book that I bought in the 90s and never used it, and I could use it now. So that was the real purpose of back to Jennifer's question. There's and to yours. There are these database providers out there now. There probably will be new database providers coming in. But when I'm talking about them, how they're out there now is it's for this TV white space area. There's other spectral bands that could potentially be operated, and that might not be a company. Right now, there's a set of companies do it. There could be spaces where this is actually run by the government, for example, and for justifiable reasons as to why that might be. For example, public safety. And the one question that we had when we were back in about 4 or 5 years ago, when this was all being stood up, the question was, how should they share with each other? What should be the cooperation between these entities? Because if they're sharing with each other, we're going to have a much better system, but they're incentivized to not. So how do you play that out? And what does that, what policies might be in place there to make that make more sense? And then there's the ultimate, which is, well, wait a second, wouldn't it be great if the incumbent operators also actively populated the database, if they were participants in this thing that we think of as sharing? Now that's a heavy lift because there's very little incentive for them. But you know, the other model here would be, well, why don't we just specify the next band that's kind of the obligation, that you participate in the shared environment. I'll tell you, the first thing that we'll do, the spectrum auction, will bring in a lot less money because they'll be like, oh, that's a hassle. I don't want to do that. It's a hassle. You've obligated me to do something I didn't want to do. I want my exclusive spectrum. Give me my exclusive spectrum. Let me go build my 4G, 5G. But what if the incumbents participated and said, you know, we're able to share that information? Of course, there's also the question of, in any of these scenarios, what does it mean to share this information? Is there privacy concerns? Are there, you know, surveillance concerns? So these, I mean, there's tons of public policy things that are just right under the surface here. That, yes, Paul.
I'm surprised that you said that sharing might disrupt the value.
Oh, it will.
Yeah, it will.
Oh, yeah. Did I say might? I mean,
well, I thought that was the whole idea. That in fact, that hypothetically, it could drive the value of the spectrum down to virtually nothing. I mean, if we...
well, how do you measure value?
Well, I mean, in terms of price.
Academic question.
If you kind of imagine that we didn't have this sequence, this really path-dependent process where we, a century ago, began setting up these exclusive zones. But if now we were starting fresh and we didn't have these zones, and instead you could start with a technology like this, wouldn't there be no price on the spectrum? Right? I mean, it would just, you'd have you'd have a cornucopia, you'd have a superabundance, and no need to price it.
Yeah, potentially. There's a thought exercise we ran as well, which was, what if we greenfield the spectrum? Let's throw out all the costs. Let's just say, what if we could start all over? How would we place things differently? Would that allocation be adjusted in a lot of different ways? And where could we put these swaths of spectrum that would really decimate the auctions? Because we do realize that. I mean, of course we realize that if you made 1,000 megahertz of spectrum available, of federal spectrum in the 1 or 2 gigahertz, why would you do auctions anymore? You'd be like, there's a plethora of available. So, yeah, I shouldn't have said might. Of course, it will, sharing will. But here's the thing that keep in mind: it's not an absolute either. I believe, you know, we already have some sharing. We're going to have some more sharing, and we'll have some more auctions, and auctions will still be bringing in a ton of money because they'll maybe even more because it's going to get harder and harder to get exclusive, you know, 10 to 20 megahertz of spectrum. So we might see the price of the auctions go up even more. But at some point, you know, even in the AWS, there was sharing. So there was sharing with Department of Defense at some level. But
So let's take one more question.
So maybe following with this question, you mentioned that new spectrum is being opened up in a millimeter wave at 2840 for 5G, for example. And while we're still in the early stage, do you see that effort in opening up that larger swaths of the spectrum, sort of a sharing environment, or are those also sort of continuing the legacy of partition?
I think a lot of that upper spectrum is going to be used in a shared way, just because of its physics, just because of its, you know, what it does to that, or this, right? It stops. There might be bands with that, but there are already bands that are allocated and assigned in, you know, microwave and other such things right up in that space. So it's not, it's not like I'm going to say, oh, that's all going to be a free for all. But I think we're going to see allocations up there that will be very much like the 2.4, with the idea of, well, this isn't about me communicating to a device outside of my home. This is about me communicating over a short hop at super high, you know, super high, you know, maybe a gig or 2 or 10, right?
Thank you.
Thank you. And like I said, any more technical depth, I know you probably, the white space people back there will have some questions for me. Happy to take them. Easy to reach me at sicker@cmu.edu. Okay? Thank you.